All right, so let's get started. Today I want to start with a question. That it's a question of probability and integration. Suppose we have a multivariate Gaussian, like this one here. So it's a distribution over y. The variance is governed by the covariance in this case, which is sigma. And then the mean is x theta. So this is precisely the Gaussian that describes the linear regression problem when we do our probabilistic version. Now, we know that this is the probability of y, assuming that x and theta are given. Okay, so that's what that bar means. We know that a probability sums to 1. Okay, so I think most of us are happy with that fact. So the integral over y of the probability must be equal to 1. If that is the case, and here is the question for you guys then, what is the integral of this function, of this exponential?
It's going to be 2 pi sigma squared to the 1/2.
Exactly. If I know that this integral which is this integral is equal to 1, this doesn't depend on y, so I can take it out of the integral, sort of basic calculus, and then I just move it to the other side. And so I get 2 pi sigma a half. Okay. So that's using basic calculus. If you have a constant inside an integral, that constant can go out, and then you can move it to the other side. If it's dividing, on the other side it multiplies. The determinant is a scalar. Okay. Now, I noticed in 340 that quite a few people were not able to answer this in the final. And I think that the problem is not to do with the intuition of what you're doing, that probability sums to 1, and therefore the thing before it is the normalization constant. But what I believe students, and most students here did not take 340, by the way. I keep saying 340, but there's only like a handful of students from 340 here. Most of you are grad students from bioinformatics, computer science. There's a few students here from statistics. There's quite a few from engineering. There might be a few from neuroscience, physics, and so on. So it's a pretty diverse crowd here, because machine learning is really a very interdisciplinary problem. And I think the reason why some people struggle with this is because of not understanding these symbols. It's not to do with machine learning. It's to do with what you learned in first year and second year, or whatever you studied, Waterloo or UBC or Toronto or whatever you did, your undergrad degree, IIT. And so if you do not understand the symbols, I will last time make this plea. Come to office hours so that I can help you by explaining this slowly and so on. All right. So office hours is the right place for me to take all the time in the world to explain to you the basics. In class, I cannot go into the basics of linear algebra and calculus because that's not what this course is about. I think everyone's on board with that. We will use, of course, I'm not just putting this fact here to point this out. I'm putting this here because actually this turns out to be an extremely useful fact. There is an alternative to maximum likelihood called Bayesian learning. Bayesian learning, as we will see, is a problem of integration as opposed to being a problem of optimization. By doing these tricks, we're able to solve very nasty integrals. If you had to do this by hand, it would take you a page of calculations. If you know what you're doing. If not, it could take you 20 pages or 40 pages. Very easily. So it's so nice that by using this trick that we know the probability sum to 1, we can actually write down the answer to these big integrals. That's actually going to be extremely useful. So you actually will not need to know your calculus and how to do integrals and so on. Even without knowing the calculus, just the common sense that a probability sums to 1 will allow us to actually solve a lot of integrals by hand. When we can do those integrals by hand, and we certainly can do them with Gaussians, and that's why we focus on Gaussians, we can do them with a few other distributions, Poisson, Dirichlet, and so on. For all those cases, one can develop machine learning methods. Those machine learning methods are actually widely used. Their examples include factor analysis, which I think a lot of people in bioinformatics use, certainly used a lot in psychology. You can do Kalman filters, which is sort of component of any adaptive filtering course in engineering. Or if you want to study tracking or robotics, that's an essential algorithm you have to learn about. That's essentially follows from this and the use of Gaussians. In fact, today's class is part of the derivation you would have to do if you're deriving Kalman filters. It appears when you use Dirichlet distributions, which I haven't discussed yet, instead of Gaussians, we can also do these tricks, and that's the basis for topic models that are used for information extraction and natural language processing. So one of the most useful techniques out there on the web for language modeling. So you can actually do a lot with models where you can apply this trick. The nice thing is that then we will be able to actually do Bayesian learning for a large class of interesting problems. For some problems, however, it is impossible to solve these integrals. In fact, the computational complexity of solving these integrals is something that it's called sharp P. It's kind of equivalent like NP hard. Solving integrals in high dimensions is not an easy problem at all. And so and that happens, for example, if we're doing a neural network, if we want to do Bayesian learning for a neural network. In that case, we will have to introduce novel techniques. In particular, we'll discuss Monte Carlo simulation in this course as a way of solving integrals. But there is this class of distributions, just this magic class, which includes the Gaussians, for which we can solve the integrals by hand, like we just did there. Okay, so I'm going to take now a step back to go over, to finish some of the things I was pointing out in the last class. So we'll continue doing linear regression. And again, because if we can do linear regression, it will be obvious that we will be able to do nonlinear regression. The principles, cross-validation, regularization, they all carry through. So if we learn them with linear models, then we just need to do a bit more work with nonlinear models, and we'll still be able to use all these ideas. Okay, so in a standard linear model, we assume that our data was, in this example that I went over, we assumed that the data was produced by a quadratic model. And then we used a quadratic model that only looked at the data to try to infer the function again that is given some data. And so the experiment that I then ran, actually I didn't run this experiment. Kevin Murphy, the author of the book that I recommend for this course, ran this experiment. These plots are from his book. What Kevin did was he increased the size of the training set. And as you increase the training set, we see that both the training error and the test error converge to the optimal error. And we'll always make some error because it's impossible for a quadratic to fit all the points because there is noise in those points as the picture indicates. If you have the right model, learning happens very fast. Okay, in both the test and training error go to 0. If your model is too simple, for example, if you now, for the same points, we try to fit a linear model, so now y hat is just a linear model, the equation of a line, then a line cannot fit a quadratic. It's impossible. It doesn't have enough degrees of freedom. And so because of that, we see that there is a systematic error. There's a bias error always. And it's impossible to get rid of this error with a linear model. No matter how many data you observe, if your model is too simple, your model will not be able to capture reality. So in your homework, in fact, you'll see that the model that you're trying is kind of simple for the bioinformatics application. And so a consequence of that is that you see that the test error is indeed very high. So if you wanted to decrease that error, you would have to change the model to a nonlinear model. And in fact, for an extra 1% toward the final mark, whoever submits a good linear model will get that. Nonlinear model using RBFs or polynomials, what we've discussed so far. Okay. But in reality, when we model, we do not know whether our model is going to be too simple or whether we have the right model. So we actually have uncertainty over models. One way folks in machine learning deal with this problem is, especially in applications where data is abundant, the approach is, let's use models with lots of parameters. Because as we get more and more data, the data will constrain the space. As we see in that picture, as you get more and more points, there will be no room for that polynomial to oscillate. And so we'll get a good fit. And that's essentially what we observe here, where I'm using a model that now consists of, so it's a model for predictions, and it has theta naught plus xi theta 1 plus dot 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 plus xi theta 25. So it's a model with 25 with a 25 order polynomial, so which will oscillate a lot. But as you increase the number of data, you can see that eventually your test error goes down. The training error tends to be below because you tend to overfit on the training data when you have such a flexible model. So your model will do very well in your training data, but doesn't do well on the test. And so by increasing the number of data, you can see that eventually, even a very complex model will approximate the truth, the true model. Okay. And that's a very important sort of lesson for machine learning. That is, in this we like to do in practice. So that there's two ways to get a good model for your data. One is you put a typically use a very large model, put a regularizer, because the regularizer, and then do cross-validation to find the ideal delta, as you do in your homework. That helps find the right model complexity. But also, the more data you have, the more room it gives you to have a more complex model. Right now, the goal, the game that's being played in artificial intelligence, at least in terms of perception, of being able to understand objects and speech, is the game of data. Google is trying to get as much data as possible for the speech recognition, and trying to use as much data as possible for image recognition. And then at the same time, they're trying to build models that are as large as possible. So they're trying to. So a lot of the focus in the Google Brain project is about using many, many cores and being able to run the algorithms that we discuss in this class in those cores. So it's not new algorithms or anything, but it's just a question of scale, because they believe that the problem of AI is that we are around here, or maybe around here. Yeah, we don't have, our learning machines have not enough data. I completely agree with them. We've never built an AI system that uses as much data as I have been or any of you have been exposed to during your lives. And certainly not as many processors as any of your brains have. All right, so that's essentially this sort of an important lesson. Having a lot of data helps, but only if you have the right model complexity. And in the whole discussion of big data, newspapers, and so on, keep that in mind.
Well, the size of the training data is increasing, right? You actually train the parameters. The parameters are actually changing, or you still use the parameter data from the parameters more? You constantly just checking the error and not changing the parameters.
Oh, no, we have to change the parameters. So the question is, the data set is increasing, but am I only using a small data set to estimate the parameters? No. The idea is you're estimating the parameters from a bigger and bigger data set. And so we have recursive ways of estimating the parameters from bigger data sets. Most of the time. Sometimes we don't. But a big focus on machine learning right now is how to deal with what we call streaming data, or the streaming model of computation, where your data keeps increasing. Like imagine Twitter feeds. Twitter feeds are streams. So, or what a robot experiences is a stream. A robot goes in the world and data comes at it throughout the existence of the battery life. And the same with us animals. We just see data all the time as a stream. And so the focus is on designing algorithms that keep learning adaptively from these streams of data. So recursive in time. And I'm going to get into it later in the course. Today's lecture is going to be about this. Maximum likelihood will give you very good predictions. So if you have those red points, you'll get that black line fit, which is a nice fit. And then we made an assumption, which was that this covariance matrix sigma for regression was, not delta, sigma. Was just the identity with sigma squared and diagonal. In other words, we assume that every point has the same variance. And then you can compute that variance by maximum likelihood. I left that for you guys as an exercise, which I hope you do. So we know how to estimate this variance by maximum likelihood, and we were saying that that variance would be the same for all points. But that in a way doesn't make much sense, right? Because in a way you would want to get something that's more like what's on the right-hand side. So this is what we've done. And this is really what we want. Why do we want it? Why is the right-hand side more sense? Why do you think I like that one better?
We have more confidence about stuff we've actually seen and stuff we haven't seen.
Exactly. So over here in this area, I've seen some data. Where I've seen data, I should be confident. Where I haven't seen data, I shouldn't be confident. Okay, so I've seen data in Canada, and someone asked me, are people in Vancouver nice? I could probably say yes or no, because I've seen a lot of data here. I'd be, I don't know, yes with 99% certainty. If people ask me, are people in Darfur nice? I'm like, well, I've never met anyone from there, so I don't know. So most likely yes, but my confidence estimate should be different. In that case, I should have more uncertainty. And so we want models that do this. And this is what Bayesian learning will give us. It will give us an automatic way of doing this. And this is being able to quantify uncertainty in this way is also going to be key to decision making. If I want to have a system that is not just learning passively from data, but it's actively gathering data, then that system needs to know what it doesn't know. So it needs to have good estimates of uncertainty. Because it needs to be aware of, for example, if I'm trying to figure out what kind of candy he likes, and I'm offering him candy, and I know that he already liked the pineapple, so I can offer him more pineapple-like candies. But if I know that I've never shown him anything like a strawberry, then I have a high uncertainty as to whether he would like strawberry or not. So that it's well worth trying strawberry, just to decrease my uncertainty and learn his preferences. So it's key for the design of user interfaces And this is like a silly example that I'm using now. But for actual real interfaces, we use these ideas. And certainly for things like deciding which ad to deliver to you guys in Facebook, or it's, you know, you get the idea. It's no different than the candy example. Likewise, drilling for oil is the same thing. You want to look where you already know you're likely to find oil, but you also want to now and then sample in areas where you have high uncertainty. And so often you have this trade-off between exploiting what you already know or exploring in areas that are likely to be lucrative but where your uncertainty is high. So being able to get a model like this will be essential. All right, so that provides us with some motivation for Bayesian learning, and I'm going to start with the basics of Bayesian learning. So I'm going to first talk about what's Bayes' rule, which is used in Bayes learning, how to apply Bayes' rule to a very simple example, which I assume some of you have seen before, and then we're going to apply Bayesian learning to the linear model. So instead of doing maximum likelihood, we're going to do this completely different technique called Bayesian learning. And the trick we use, which is that we exploit the fact that we know this integral, is something that's part of a general procedure for deriving Bayesian estimators known as conjugate analysis. So I'm going to go over that too. Okay, so let's start with an example. You go to the doctor has good news and bad news. The bad news is that you've tested positive for a very serious disease, and the doctor tells you that the test is 99% accurate. The good news, the doctor tells you, is that this disease is rare. Okay, only 1 in 10,000 people get this disease. Should you be worried or should you not be worried? Should you be very worried or not very worried? How many people would be very worried? Hands up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So 15 people would be very worried. Oops. How many people would be totally not worried, totally chilled out? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So it's about 14 people would be like chill. And how many would be in between? Okay, probably about 20. Let's say roughly 20. Okay, so that's more or less our distribution. Okay, so let's see how we would deal with this problem. For that, we need to introduce, and this problem, by the way, arises not only in medicine, but this is the same problem that a judge encounters in court most of the time. You know, there is the evidence points, so there is a probability that this person committed this crime, and then you need to look at how probable that evidence is, and so on. So you need to combine these two sources of information that I have combined here, this one and this one. Most often people just look at one source of information and they ignore the other one, simply because they have not the ability of reasoning properly and knowing how to combine these two sources of information. Or they haven't been educated. This happens also a lot in sports, where cyclists, for example, test positive for having taken drugs, and then people make the judgment based on that. But they don't take into account other probabilities. Okay. to answer this, we will learn something called Bayes' rule. Bayes' rule is fundamental. It's one of the coolest rules of reasoning that there exist. It should be taught in high school, and it's almost a crime that it's not taught in high school. That's how strongly I feel about it. It's, I think, more important than knowing that F equal ma, for sure. Because it's a rule about how we humans reason and how to build optimal reasoning systems. How to go from evidence to theories. And psychologists love Bayes' rule. So there's a lot of great TED Talks about Bayes' rule. There's many TED Talks about how babies are actually very good at carrying out Bayes' rule. And unfortunately, our education systems don't maintain that. So I particularly recommend you look at the TED Talk of Alison Gopnik about this. And then there's also some great work by Josh Tenenbaum. Josh is a cognitive scientist. Alison is a psychologist at Berkeley. So in psychology, this is Bayesian thinking, especially in cognitive psychology, is sort of very important. Very important area of research. So what Bayes' rule gives us is a way of inverting probabilities. If you know the probability of B given A, you're able to invert it and get the probability of A given B. And it's the formal mechanism for doing so. Why is this important? Because, okay, let's do it just with one trivial example. How many of you have the ability in your computer devices to type a sentence and have that sentence be spoken by the computer? Okay, most of you. That's easy. In a computer, you might have a robotic voice, but these days you can even get it to have a sexy voice, or Brad Pitt's voice, or whatever. So that problem is solved. From words, we know how to generate speech. The inverse problem we don't know how to solve yet. Google's come very close to have a pretty good system, but it's taking so much effort. Okay, how to go from speech to words. How to invert that process for a computer turns out to be extremely hard. A lot of the problems we encounter in AI are these type of inverse problems. If we have vision is the same thing. Our computer graphics has got really good, especially texture mappings and so on. You go to these, we are always surprised at the latest computer CG movie where we're like, oh my God, that golem is so real. But the opposite, how to go from rules to images is easy, but how to go from easy as in, it still involves a lot of work for wet to digital, but how to go from, do the opposite, like how to go from actual images to understand what the objects are in the image turns out to be very hard. So being able to invert probabilities is key in perception. And certainly with humans as well. So there's many psychologists who studied this, who study Bayesian inference as a way of which humans and animals do perception. Okay, having said all this, Bayes' rule is just a consequence. It's essentially this formula that's here, and it allows you to invert two things. Let's parse this a little bit. A rule of probability is that the joint distribution of two variables is just equal to the conditional times the marginal. Okay, so, and it's also A given B times P of B. Okay. To get the definitions right here, let's give these guys names. So this is called the marginal. This is the conditional. And this is a joint distribution, because it models A and B jointly. Okay. My YouTube 340 lectures go in detail in examples with, say, binary variables on how we do this and so on. So if you want a background on that, I recommend that video. Now, and again, sorry about that. And this bar here means given. So we know that the integral of P of A and B over dA and dB is equal to 1, because probability sum to 1. We know that the integral of A given B over A is also equal to 1. In this case, I'm emphasizing that P of A given B is a distribution over A. It's not a distribution over B. B is being given. It's deterministic. It was an observation. Suppose we see B, then we only have uncertainty in A. And likewise, the integral over any of the marginals, like P of A, dA is equal to 1, which is just the same rule as the rule for the joint. We also know that in order to get a marginal from a joint, we integrate P of A and B. So in statistics, whenever we have a distribution over two quantities and we want to have the distribution to be only over one quantity, the right mathematical operation is to integrate the other variable. And a derivation of this is in my 340 video, my second lecture video, has a derivation of this property. So these are basic rules of probability, but they're essential in order to understand Bayesian inference. So we will make ample use of these rules. This operation here of integration in statistics, when we have probabilities, we also call it marginalization. And the conditioning that I've introduced there is also called the chain rule of probability. And so now, finally, Bayes' rule is just a consequence of the chain rule, right? Because we've said P of A and B can be written in two ways. If I equate those two black lines on the right-hand side, I get Bayes' rule.
I was just wondering, probability of A given B, dA. I would have thought that would be dB.
A given B dA. No, because let me try to give this an example. P of A and B, if I integrate of, this is a distribution of A given that you've observed B.
Oh, I see.
So that bar is very important to understand its semantics. This is saying that this variable here has been observed. Okay. Now, if I have observed something, I know what it is. There is no uncertainty about it anymore. That is a deterministic variable. And so when you see that bar, I want you to think of it as a context. It's P of A given B. B could be the country where you are. So A might be, say, a variable that measures temperature. Temperature is a good random variable. P of A is temperature, B is the country. And so I can talk of P of A given B in Spain, and P of A given B equal England, and so on. Once I observe the country, I know what the distribution over A. Each country has this particular distribution over A. And for that distribution, when I sum over, I get 1. So think of or another example. For each country, you build a histogram of the heights of people, and you normalize, so that each country now has a probability distribution over the heights of its individuals. Once, then if I pick any country, the histogram in that country sums to 1. Okay. However, if I don't know the country either, if I have uncertainty as to there's an individual, I don't know what country the individual is from, then I need to sum off the countries as well. And that would be the other calculation that I had on top there, summing over A and B. But yeah, the bar, anything to the right of the bar has been observed. It's deterministic. There's no certainty. There's no need for probability to deal with things we know. Probability is only used for the things we don't know. All right, how do we, here's now how this is used in the process of inference, which is essentially the process of inference is a process of we having hypotheses in our head, making observations, and updating our hypothesis in light of the observations that we've seen. Okay, so I have a belief about religion, say, I observe some data or a documentary about religion, and then my updates about religion get updated, or about anything else. So we have some prior beliefs, and as a toy example, think of a child that has a prior belief as to what a sheep is, and it might think, well, goats kind of look like sheep, that must be a sheep with low probability. And then, you know, she's going to the countryside with her parents, and the parents say, look, Alice, there is a sheep over there, and they point to it, and so she gets a label. So we have parameters of, she had a model, but now there's a likelihood because there's data. So she has the probability of the data given the model, or the hypothesis in this case, in blue, in the equation and in the plot. And then what Alice then does is she combines the likelihood with the prior by using Bayes' rule. And she gets the posterior, which is her new beliefs as to what a sheep must look like. Okay? And this, just to emphasize, is P of D given H times P of H using Bayes' rule divided by P of D. Okay, because if I this quantity here is P of D and H prime. If I integrate over one variable, I get rid of it, and I get back P of D. So that's just a straight application of the rules we introduced. So that's the basis of Bayesian reasoning. The only problem is we're going to have to deal with doing the sum always. For most problems of interest, that sum, for a great many problems, that sum is actually combinatorial. So it's equivalent of NP hard, or happens to be a continuous integral for which we do not know how to solve it. And often it's an integral in high dimensions. Like, for example, when I write this, this is actually the integral over the vector y. So it's an integral over, if you have n observations, it's an integral in the n-dimensional space. If n is a million, it's a million-dimensional integral. And that's not easy to do in practice. For Gaussians, however, we can do it. This could be in a trillion dimensions, and the answer is that. That's the beauty of that trick. Okay, we'll ignore that for now. Okay, so let's go back to our diagnosis problem. So the probability of the test being positive, of the test being accurate, that is the probability that the test is true given that you have the disease, or that the test is false given that you have the disease, is 0.99. D denotes disease as a random variable, and T denotes the test. I also said that the disease only affects 1 in 10,000 people. That means the probability is 1 over 10,000, or 0.0001. In order to know whether you actually have a problem or not, we just compute, we just apply Bayes' rule. Given the test is positive, what is the probability that I have the disease? And the two sources of integration, the two sources of information I need to integrate are what is the probability of the disease in the population, and and what is the probability of the test being accurate. And if you do that, well, then it's just a question of plugging in numbers. This is just 0.99 times, what's the probability of you having the disease? 0.001. If anyone has a calculator, this would be a good time to get it out, because I will need some help. And then we have the probability. We know that P of t equals 0 given d equals 0 plus P of t equal 1 given d equals 0 is equal to, right? Given that you're in Spain, so d equals 0, d is equal given. The context is being given. And since t can either be 0 or 1, if you sum over the two things that t can be, it has to give you 1. The probability has to sum to 1. So this has to be 1 minus 0.99 times the probability that you don't have the disease, probability of d equals 0, which is just 1 minus 0.0001 plus 0.99 times 0.0001. Can someone calculate this for me?
0.0098.
Okay, that low?
Yeah.
Okay, how many people would now be very worried? 5 people. I would still be very worried if this was like cancer or something. Even if it's 1 in 1,000, I might still not be too happy. But at least now I have quantified a bit better whether I should be worried or not. And surprisingly, if you actually Google Bayes rule in Google News, you'll find that there's many articles about Bayes rule. There's even an article about Bayes rule being banned in courts of law in England last year or the year before. And mainly because judges were arguing that common people cannot reason in this way. Now that's really sad, because we're throwing away reasoning just because of our inability to learn basic math. So math is important, not just as a way of communicating. And I just use math because that's my way of communicating quickly an idea in machine learning. I could stand here and just go over the whole course of machine learning without a single formula, but it would take a lot longer to do it. And so math just makes things easier to communicate. But it also helps us with reason, to reason about simple facts that are beyond just technological things. Okay, so this is essentially now an application of this. This is how speech recognition works. You want to infer the probability of words given the sounds that you hear. We do have good models to generate sounds given words. In the old days, this slide needs to be updated. In the old days, we used to use mixtures of Gaussians as the likelihood. These days, we use deep nets here. That's why in this course I will be teaching you about deep nets and not mixtures of Gaussians. Even though mixtures of Gaussians are useful models. And then for words, the language model is actually people use simple things. For example, they use bigrams, which is essentially how often do pairs of words occur in the English language. For that, you just get a big collection of text documents, and you simply count how often does this word follow this other word. And with that, that's enough for you to be able to predict which word goes next. For example, if I say the silence of the, most of you know what the next word will be. Right? All right, so Bayesian learning. We will manipulate Gaussians, we will manipulate neural networks, different distributions. But in an abstract way, we will always be doing exactly what's on this slide. We will start by defining a likelihood, which is the probability of the model parameters given the date. In this case, I said let the data just be a bunch of x's, x1, x2, where each x could be, say, a coin flip. the data could also consist of pairs of observations, inputs and outputs, like linear regression. And we'll see that example soon. And the other thing we do is we specify a prior. Now, a prior essentially indicates two things. It might indicate our uncertainty over the parameters, and so in a way, by indicating uncertainty over the parameters, by using probability of the parameters, we're saying that our beliefs over the parameters are subjective. Okay. So Bayesian inference, unlike maximum likelihood, for example, does not believe in this concept of this true theta in finite data cases. As the data goes to infinity, the two actually match. But in the finite case, what we're saying is theta is a random variable. For maximum likelihood, theta is not a random variable. For maximum likelihood, the randomness is in the data. Okay, so it's P of y. The randomness is in the y's, not in the theta. Theta is just a parameter. In Bayesian inference, we are putting a distribution of a theta, so we're acknowledging that there's uncertainty. Now, that prior distribution can also be understood as my initial beliefs. Okay, just like in that example with the sheep and the goats and Alice in the countryside. And so I will choose a prior that encodes my beliefs about the problem. Okay, so this is natural for a robot, where I can put in some basic prior knowledge in a robot and then let that robot go into the world, and that robot will gather observations and update its knowledge. The robot updates its knowledge by doing Bayes' rule. And that gives us something that we call the posterior distribution. So it's a posteriori inference. So the posterior distribution essentially follows by multiplying the likelihood times the parameters. And this also I will write as P of D given theta times P of theta. And this symbol here means proportional. In other words, up to a constant. P of D is a constant in terms of theta, because it doesn't have any thetas in terms of the posterior. And in fact, P of D, like in this case, is just the guy that normalizes the distribution, that makes it sum to 1. Because, in other words, P of D is equal to the integral of P of D given theta times P of theta d theta, which is equal to the integral of P of D and theta over theta. So again, if we have a joint distribution over two quantities, we integrate one, we get the margin. And that makes sense, because P of theta is an integral of a theta, because we know that the integral of P of theta given D over theta is equal to 1. So for this to be true, it must be that the denominator in the expression on the right-hand side, that is P of D, must be the sum of what's in the numerator, of all the options in the numerator. That ensures that the quantity sums to 1. Okay, the denominator normalizes the denominator. So it's just a sum over all the options below. And that ensures that the quantities, everything sums to 1. All the probabilities sum to 1. Okay, so that's essentially the general framework. We need to specify a likelihood, and we need to specify a prior. And in that prior, we will be able to put our preferences. So we're not just going to pay attention to the data, but we're going to use all sorts of prior knowledge. Okay. That prior is important to make statistical decisions. Like, let's say, for example, let me put that following example. I'm going to do a test with you guys. How many of you, what do you think is the probability that I will take a job at some other university this year? Anyone? Let's start with you. Sitting in front gets you that.
3%.
3%. So I'm going to write those probabilities. Someone from the back. 40%. Yeah.
50%.
50%. Wow.
1%.
0.01. Okay. Now, let me ask you a different question. So, you're able to, actually, before I ask you a different question, let me say something about this. You're able to assign probabilities, and each of you has a different probability estimate. Hence, probability is subjective. Your prior beliefs are different. This is why we introduced that extra p of theta, to model that. You're able to assign probabilities. Moreover, you are able to assign those probabilities without having ever seen me leaving. Okay, so it's not like when I ask you, what's the probability that the coin will be tails? Your answer would be, it's going to be 50%, because if you take a coin and you toss it 100 times and you observe, that is, you gather data. So that's the frequentist view. You look at frequencies of occurrence of something and you use that to say what the probability should be. And as the number of coins goes to infinity, i.e. in asymptotics, the counts of how many times it should be heads, it should converge to the true expectation, which is 0.5. And that's basically the law of large numbers. Bayesian learning deals with this other case where you have to deal with a problem for which you have absolutely no previous repetitions, because you've never seen me leaving this university. You haven't counted how many times I've left and how many times I haven't left. And yet you're able to assign probabilities to that event. And it's based on your own preferences, based on your whatever knowledge, and so on. Okay, so now let's do an example. This example involves quite a bit of algebra. I'm going to do it in class, and it's for linear regression. How do we derive the posterior for linear regression? This turns out to be also your homework exercise question 2. So in doing this in class, I'm kind of doing the homework for you. But I still want you to go and do it, because it's only when you do this by yourself that you actually get to appreciate this. Now, the calculation I'm going to do is very tedious. It's basically called completing the square. Some of us have seen this before. And how many of you have seen that before? Completing squares. Yeah. So it's essentially basically an application of completing squares. And it turns out that it's what you need to know in order to derive Kalman filters and factor analysis and linear regression and all these models. Okay. So what I'm going to assume, and I'm only showing you here with 1D distributions because it's hard to plot this for high dimensions, but we know that for linear regression what our likelihood is. Okay, so we've already spent quite a bit of time on the likelihood of linear regression. And if we maximize that quantity, that probability, we get theta equal x transpose x inverse x transpose y. Here we're going to do another thing. We're going to add a prior, p of theta. And that prior is a distribution of a theta. That prior is going to have a mean theta naught and a variance v naught. To sort of kind of get to the end of the exercise, at the end of the exercise I will show you that if you make theta naught equal to 0, and if you make v naught be a diagonal matrix, you get ridge regression. So the Bayesian framework will subsume, in this case, maximum likelihood, and it will also subsume ridge regression. It's a more general framework. However, instead of just computing a single theta, what we will compute is a distribution over the thetas. Okay? So we're going to compute a posterior distribution. This guy here, which is the green guy in the picture. That posterior distribution also acknowledges has a mean, but it also has a variance that acknowledges, models the uncertainty in the thetas. And that's the game. Going back to that original picture I showed you at the beginning of class, our game will be to be very good at knowing uncertainties. If we know uncertainties, we will know which candy to offer him. Okay, so the next exercise, what I'm going to do next is I'm going to show you that if I take the prior and I multiply the prior times the likelihood and I solve the integral at the bottom using this trick here, I will be able to derive this expression, which is essentially the posterior distribution. And that's the exercise that I've given you in your homework. In your homework, I also asked you to do one more thing, which is let's assume that sigma is unknown, and let's put a prior on sigma. What is the posterior of sigma? Okay, but if you know how to do it for theta, for sigma, you just follow exactly the same procedure. And this completing the square stuff that I'm doing now is basically called conjugate analysis. And what conjugate analysis means is that the prior and the posterior have the same shape. If my prior is Gaussian, I will show you that, that the posterior will also be Gaussian. For the variance, and in fact for the homework I gave you the more interesting case, I allowed each point to have a different variance. So I gave you a full matrix sigma. And in that case, you will put a prior on matrices. Okay? As I pointed out in that homework, a prior over a matrices, where the entries have to be positive, is known as the inverse Wishart distribution. So if you go to the Wikipedia page for the inverse Wishart, it tells you all the properties. What's the mean, what's the peak, and so on. You will then see that if you take an inverse Wishart distribution and you multiply it times a Gaussian, you get an inverse Wishart distribution. And that's the answer that I want you to compute. And that's essentially what I mean by conjugate analysis.
Do you use the conjugate, like, are they from the same family just to make it easier to manipulate?
So throughout the last 50 years, 60 years, people have figured out a class of distributions. We actually call it the exponential family. And for that class of distributions, we can do conjugate analysis. You can't do it for all distributions, but there's recipes. So like if you take a course in Bayesian statistics, you will go over each case. So we can do it for Gaussians, we can do it for inverse Wisharts, and the univariate version of the inverse Wishart is the inverse gamma. And you can do it for Poisson, and so on. So there's a few cases where we can do that. And any book on Bayesian analysis, if you search conjugate analysis, it will tell you which of these cases.
That way to exploit this.
Exactly. So I'm in a way cheating.
Okay.
Because I'm designing my prior to be of the right shape. Whereas in practice, I would like to be very flexible in how I choose the prior. But how to come up with if I come up with very flexible priors, I will not be able to use this trick. Because then I will have to do the integral in high dimensions by numerically. And so sometimes it makes more sense to accept a model that might be not the best model, but for which computation is easy, as opposed to come up with the best model and have computation take you a zillion years to produce your answer. So there's a trade-off there. Okay, let's see first how we do this. So we're saying that we start by saying that our posterior is given the data y and x and the variance. I'm going to assume that the variance is given for now, is proportional to the likelihood, which we know what it is. Okay, it's essentially that expression there, times that prior, p of theta. Okay, and this is like at the same time, it's proportional to e to the minus 1 over 2 sigma squared y minus x theta transpose y minus x theta. So that's the likelihood that we've had for linear regression. And I just use proportional here to get rid of that 2 pi sigma, because that's just a constant. Okay, so this doesn't depend on theta. The posterior distribution is a distribution of a theta, So if I put a proportionality constant, if I change this equal to a proportionality, I can get rid of this constant. And of course, the prior is e to minus a half, and has mean theta naught and covariance v naught. So the prior has mean theta naught, covariance v naught. Now, the game that I'm going to play is I'm going to complete squares. I'm going to combine these two terms. And then I'm going to argue that when I combine those two terms, I will get something that looks like this. And then because I know what the integral of this is, I will be able to put the constant. So what I'm going to first try to do is manipulate these quantities so that I end up with something that looks like this, that has a single Gauss. All right, so how do we do that? So I'm going to rewrite this as e to the minus a half. And of course, if I have e to the a times e to the b, that's just e to the a plus b. So I'm going to combine the two terms in the exponent. And so I have y minus x theta transpose y minus x theta plus theta minus theta naught transpose v naught. And let me know if I make any mistakes, because I typically make mistakes when I do this derivation, because there's lots of indices.
Sigma squared.
Already made a mistake. Okay, let's put it back there. Okay, so what we need to do next is take the product of some of these terms. And so I get sigma minus 2 y transpose y. And then I will get minus 2 sigma inverse 2. And then I have the cross terms of this guy, which is y transpose x theta. And then I have the quadratic term when I multiply this times this. And that's just theta transpose x transpose times sigma minus 2 x theta plus theta transpose v naught minus 1 theta minus 2 theta naught transpose v naught minus 1 theta, and then finally plus the last term, which is theta naught transpose v naught minus 1 theta naught. Okay? Now, what you do then, and the reason why I'm doing this in class, even though this is very tedious, is because it's going to help you with the homework. And also because this is one of those calculations that when you do Bayesian learning, you really have to do this over and over again. So if one of you has the fortune of ending up doing Bayesian learning for factor analysis, for anything that involves Gaussians in your master's or your PhD, you're going to have to do this calculation. It's one of those ubiquitous calculations. And so I can now rewrite this as e to the minus a half. And I can just look at all now I'm going to group terms. So I'm going to complete squares. I'm going to group all the terms in theta squared, basically theta transpose theta, the terms that are linear in theta, the theta terms, and then the other terms, the constant terms. For the constant terms, I'm just going to call them const. Because I'm working up to proportionality, so in a sense, I don't need to keep track of what the constants are. Minus, and so let's group terms. So now if I group terms, I would have plus. Okay, and here I do want to, I think it's a good idea to use colors. Whoa. No! No. Technology has failed us really too much. If anyone knows how to save this, this is the time to do something. All right. So much for my smooth derivation. And task. All right. I'm gonna do some magic now. Which lecture was it last year? Yeah, we've recovered. All right, but in recovering, I've added a few extra steps. Okay, so where were we? We had done this step here, and I had done this step. This is where we were. And so what I'm doing here is I'm taking the quadratic terms, which are this guy, and what was the other quadratic term, which was this guy. So this is terms that involve theta twice. And I'm grouping them into a single term. Okay? So the thing in the middle here is just that sigma squared times the identity. The quantity here is just V naught. And so I just need to add it to when I group them. I'm also going to group the... Let's do what cyan. I'm also going to group the terms that only involve one theta, which would be this term here and this term here. And that gives me this term here. Okay? So the first thing I do is I just group the terms that involve theta squared, and then I group the terms that involve theta, and that leaves me with now an expression that's a quadratic. Now, in order to simplify writing this, I'm going to call this Vn minus 1. Okay, so that's just the name I'm giving it, that to not have to write the whole thing ever again. And so at the next step, all I'm doing is I'm writing Vn minus 1 there instead of writing the long expression. Everything else remains the same. Sigma inverse is the same as just dividing by sigma squared. What I do next is the trick, the beautiful trick. What I'm going to do is I'm going to subtract and add the same term. Okay. The reason why I'm doing this is because if I look at let's say green. If I look at this and this and this, these three terms, I can see that that's what I would obtain if I were to have a Gaussian distribution that has mean theta n and covariance Vn. So that would give me a posterior distribution because it's a distribution of a theta, which has a mean and a variance. This is a constant, which doesn't matter what it is because I'm working up to proportionality. And so the only thing is there is this nagging term here. That's a bad term. So I want to get rid of that term. Because if I get rid of that term, then I end up, I'm going to rewrite this in a slightly different way. If I end up with an expression that says it's proportional to e to the minus a half p of theta given x and y and sigma squared is proportional to e to the minus a half theta minus theta n times Vn minus 1 theta minus theta n, which is the same as saying that it's equal to a constant times e to the minus a half, that whole expression there. Okay. If I can make this expression, massage it so that it looks like this, then I will know what this constant is, because that constant is what must make this sum to 1.
Yeah, I think you meant to put the green line under the other orange one.
Under the... No,
Next to last line.
next to last. Now I think this is right. I have a quadratic term. In order to get the next guy, I'm going to use a quadratic term. The negative term in theta, because there's a minus.
Another negative term.
Sorry?
Another negative term.
This one?
Yeah, then you look at the next term.
Wait, I'm not following you. This term, you would want? So let's count terms. I have const is 1, the quadratic is 2, 3 is the next one, 4, and 5. Which one are you pointing to?
Well, I guess it doesn't really matter. Just how you think of the constant.
Yes. I mean, the constant is just, I can write a constant is a constant plus a constant. I can manipulate the constant whichever way I want, yeah. So it wouldn't matter. But, and so this is true because if you multiply this guy here, you just get theta transpose Vn minus 1 times theta, and then you would get minus 2 theta and transpose Vn minus 1 theta, and then you would have a constant term, which is theta n Vn theta n, which are not, theta n and Vn are just quantities. Where theta is the random, is the variable. So if I multiply that, that's what I get. So that's why I grouped those. The terms that I underlined in green were the terms that I grouped in this expression. So the only thing that remains is for me to get rid of this guy here. Because if I get rid of this, then I know what this constant is, right? So what's that constant? What must it be? I want everyone to write this constant down. I will finish this in the next class. And I want you to recall the following property of Gaussians. If I integrate the Gaussian, it doesn't matter what symbols I use for that Gaussian. The integral of a Gaussian is 1. Right? So if that's true, then what must be this for P of theta to be a valid distribution? Yeah, some people are pointing out to it. So it's just a normalizing constant, which is 2 pi Vn minus a half. That's what we need to put there. Because if I put that there, that particular constant ensures that I have a probability distribution. So it's that trick, that simple trick is what we're exploiting. That we know the integral of a Gaussian. We know that the Gaussian integrates to 1. We know that this guy is the thing that makes those distributions sum to 1. It's the right, it's the integral at the bottom. So what I'm going to show you in the next class quickly is how we get rid of this term. And essentially, you will have to actually do it before the next class because it's in your homework. You get rid of it by just solving for theta n. We haven't said what theta n is. Theta n is just now an arbitrary thing that we've introduced. If you solve for theta n, you'll get the theta n that ensures that that term vanishes. And that theta n that ensures that the term vanishes is the theta n that is in this expression. And that finishes essentially the Bayesian linear regression. Actually, just very quickly, I might as well get done with this. And I promise I will make it go easier next time. If you choose theta naught to be 0, and if you choose this covariance to be a diagonal, you get ridge regression. The posterior mean is just a ridge regression estimate. So we recover ridge regression. And if you choose lambda to go to 0, that is if you make the prior distribution flat, if you basically say my priors I really don't know what this theta should be, you get maximum likelihood, which is when you don't have subjective opinions. Okay? In the next class, I'm going to go over the predictive distribution, which is the way you calculate these intervals. All right, see you guys next week. Good luck with the homework. Come to my office hours after this class.
Okay.